Hello students, I am Dr. Vidya H.A. from Global Academy of Technology, working as Professor and HOD in the Department of Electrical and Electronics Engineering. So today I am going to teach that is DC machines. These machines are rotating magnetic machines because this will follow the dynamically induced EMF, and also these machines are also called as electromechanical systems. Because these machines are used to convert the mechanical energy into electrical energy and vice versa. If the DC machine is used to convert mechanical energy to electrical energy, this is called as generator. If the machine is converting the electrical energy into mechanical energy, this is a motor. That is why these machines are called the electromechanical systems. So, and also I already told you that this we are going to call it as rotating machines because this will follow the dynamically induced EMF concept. There are two types of induced EMF. One is dynamically induced EMF, another one is statically induced EMF. This I have already studied in module 1. So, under statically induced EMF, the transformer will come. Under dynamically induced EMF, all the rotating machines will come. Okay. Now, I will explain to you how exactly this dynamically induced EMF is this generator and motor principle, how exactly these are working with the dynamically induced EMF by considering the concept what are the minimum requirement to generate the induced EMF and also the working principle of DC machine as a motor and also as a generator. The construction principle of generator and motor both are same. Only thing is, so we are going to use, that is Fleming's right hand rule for generator, Fleming's left hand rule for motor. So, the essential requirements are conductors, magnetic field and mechanical energy. So, generator converts the mechanical energy into electrical energy. Now, I will take the example and I am going to explain how exactly the magnetic field is produced. So, how exactly we are using the conductors and magnetic field to induce the EMF. So, there are two poles, north and south. The flux lines will start from north pole and it enters the south pole like this. The magnetic field can be produced by supplying, since it is a DC machine, we can use that DC source to produce this magnetic field. Here I will consider this conductor is rotating in the magnetic field because the EMF will be induced whenever there is a relative motion between the conductor and the magnetic field. Now, you think this as a rectangular conductor. So, this has one side, this has another side. I will consider this is AB, CD. So, now when it is rotating in the magnetic field, so how exactly the EMF will be induced? According to Faraday's laws of electromagnetic induction, Faraday's first law states that whenever the conductor cuts the magnetic field, the EMF will be induced. The second law states that the EMF induced is directly proportional to rate of change of flux linkages. Okay. When the maximum flux will be linked to this, so to to this conductor when it is exactly, when the axis of the conductor is exactly perpendicular to this, the maximum flux will be linked. Suppose if both the sides of the conductor is along the parallel, it is parallel to the magnetic lines, here the magnetic flux lines cut by the conductor is 0, the EMF induced is 0. Whenever this conductor moves in this magnetic field, so what will happen? This magnetic flux lines cut by the conductor increases. At this point, the maximum this flux lines will be cut by this conductor, and when it rotates like this, see, it is decreasing. The number of lines cut by the conductor is decreasing. When it is at 180 degree, again it becomes 0. Means, so I have started this position, so south to north, so it is rotating in the anticlockwise direction, and then so here it will come under the influence of north pole. So after 180 degree, this direction is going to change, okay. So and then at this point, once again this angle is 270 degree, the maximum flux will be linked with this conductor, and when it starts rotating in this direction, so it completes one full revolution, that is 360 degree. So at this point also the EMF induced is 0. So how exactly you are going to represent this? When you are considering this theta is equal to omega t, where theta is the angle between the relative motion of the conductor and the magnetic lines. So this will be theta. So when you are going to consider this theta in the x axis, when you are taking this E, the induced EMF in the y axis, I already told you that when the axis of the conductor and also the magnetic lines are parallel to each other, the EMF induced is 0. So it will start from here, and then at 90 degree, when both are exactly perpendicular to each other, the EMF induced is maximum. And then when it starts moving from 90 degree to 180 degree, so it is going to decrease. So this is 0 degree and this is pi by 2, that is 180 degree pi. After 180 degree, this EMF induced, the direction of induced EMF is reversed. So this is minus this 180 degree to 2 pi, it is negative. So this we are going to call it as positive half cycle. This is the negative half cycle of the induced EMF. This is how, by using the conductor's magnetic field and the mechanical energy, so the EMF is induced here, okay. And then, so to find out the direction of this induced EMF, we are going to consider that Fleming's right hand rule. So this is what, and also when we have provided the closed path to this conductor, the current will flow due to the induced EMF. Here we can provide any load or the meters with small resistance, we can connect it, okay. When we are providing this closed path, the current will flow in this particular circuit. I already explained this working principle of DC machine as a DC generator. It works on the principle of Faraday's laws of electromagnetic induction. Whenever a conductor is moved in the magnetic field, an EMF is induced, and the magnitude of induced EMF is directly proportional to the rate of change of flux linkages. This EMF causes a current when the circuit is closed. So now you consider this rectangular coil, whatever I have explained with this scale. So here we have considered the rectangular coil in between this north and south pole, okay. Whenever this supply is given by the DC source, the magnetic field will be produced, the magnetic lines will start from north pole and it will enter to the south pole. in that magnetic field, whenever this conductor is moved, you see this conductor, it has two sides A, B, C and D. So here in this, it will rotate with respect to under the influence of north pole and south pole. We have shown this rotation of coil is in the anticlockwise direction. When it is rotating in the anticlockwise direction, it will start from 0 degree and then 90 and then 180, then once again it will start the rotation from north to south, that is from 180 degree to 360 degree. So that is to create a magnetic induced EMF, the relative motion between the conductor and the magnetic field is required. So here when I am going to see this, so the EMF generated in the magnetic field is AC, but we are studying on DC machines. How exactly we have to convert this AC into DC? So this AC EMF produces AC currents, but at the terminals we have to convert this into DC. At the terminals we have to convert this into DC. For that we are using split rings and also the brushes. So what these split rings will do? So during that 0 to 180 degree, the brush, here brushes are connected, the brush B1 is fitted to this split ring, that is with the symbol R1, and then B2 is fitted to this, brush B2 is fitted to this split ring, that is R2. Okay, and then this commutator is used, this is used to convert the AC into DC. It is similar to the rectification. Okay, so now in this direction, when it is from 0 to 180 degree, this brush B1 is fitted to this R1. So the current will flow from, it will vary, that is in this manner from 0 to pi. When it is from 180 degree to 360 degree, this brush contact will come, this and this during this 0 to 180 degree, this we will consider it is a positive polarity, and during this 180 degree to 360 degree, this brush contact will come to this R2. So this terminal will act like positive polarity. Always the position of this brush B1 indicates positive polarity, brush B2 indicates negative polarity. So during that 180 degree to 360 degree, the current is also, the current will follow this positive direction. That is why due to this alternating EMF, so at the terminals we have converted the current into direct. So it is called as direct current. That's why these machines are called as DC machines. This is the working principle of DC machine as a generator. So now how exactly you are going to find out the direction of the voltage induced in the conductor? Okay, for this we are going to use the right hand rule. So this is also called as generator rule. So when we are stretching the three fingers, that is thumb, forefinger and middle finger of the right hand at 90 degree to each other, so this forefinger indicates the magnetic field, thumb indicates the motion of the conductor and middle finger indicates the induced EMF. Okay, so this is how we are going to follow the Fleming's right hand rule to find out the direction of induced EMF. So this is also indicated with this figure. So it is clear that we are going to use this right hand rule to indicate the induced EMF by using middle finger. And also here I had given the equation, that is voltage is equal to BLV. So actually the full equation is, that is voltage, induced voltage E is equal to BLV sin theta. This theta represents the angle between the relative motion of the conductor and the magnetic field, and then V is the velocity of motion of the conductor, L is the length of the conductor within the magnetic field, and B is the flux density. So, since at 90 degree theta is equal to 90 degree, sin theta is equal to 1. So, E is equal to Em, that is equal to BLV. At theta is equal to 90 degree, we will get the maximum induced EMF. When we are considering the working principle of DC machine as a generator, here we will consider the Fleming's left hand rule. So, the Fleming's left hand rule states that whenever the current carrying conductor is placed in the magnetic field, it experiences the force. Okay? Due to that force, there is a rotation of conductor and it cuts the magnetic field. So, then the EMF will be induced. Okay? So, the Fleming's left hand rule, here the direction of rotation we have considered it as clockwise. Okay? So, for both the machines to induce the electric field, the external DC source is required. So, we are using this Fleming's left hand rule to determine the direction of the current carrying conductor in fixed magnetic field. Here in both the cases magnetic field is fixed, only the conductor is rotating. This thumb indicates the direction of motion of the conductor, forefinger indicates the direction of the magnetic field, and this middle finger indicates the conventional current direction. So, this is also called it as motor rule. Fleming's left hand rule is also called it as motor rule. When we are coming to this constructional features of DC machine, so there are two parts, one is stator, another one is rotor. Stator and then rotor. As the name indicates, stator is a stationary part and rotor is the rotating part. So, here we have the stator, so it has the frame and yoke. Okay. Here the minimum requirement for this DC machine to work is field system, then rotating system. Okay. So, here I think you are observing here there is a pole system. This pole system has the pole core and pole shoe. So, here I will tell you with this. So, this is what you have, the pole, this will be the pole core and this will be the pole shoe. This pole core is designed by this laminations. Okay. This pole is bolted to the yoke, that is the mechanical support to this machine. Okay. So, here these poles are bolted to the, that is frame, that will be the mechanical support, and then at the end you will have that end plate to give that full support. And I will show you that how exactly the rotating part is there. This is the armature part. Okay. This armature, see here how much it is thin, it is around 0.5 mm thickness. Okay. So, here these are laminated to each other, like this you will have several plates. So, these are laminated to each other to form the armature core. Okay. See, at the outer periphery these are slotted. Here we are going to place the conductors. So, when we may consider, see, when you are going to place here that pole shoes, you are going to consider so these poles are fitted to the frame. So, if you have 4 poles, you will have that the structure like this. I already showed how exactly the pole will be there. It has 2 parts, pole core and pole shoe. Here you have this rotating part, that is called armature. Here the outer periphery, here it is slotted. Okay, you are going to place the conductors here. If it is all the conductors will be under any one of the pole, it may be under north pole or it may be under south pole. So now what exactly you are doing is, to make a winding, the conductor at this, you are going to connect it to the conductor under the south pole. The conductor under the influence of north pole, you are going to connect to the conductor under the influence of south pole. That you are going to consider it as one turn. So here conductor under the north pole, you are going to connect to the conductor under the south pole like this. This you are going to consider it is one turn. So this is how you are going to form the windings. Later I will explain to you what are the different types of connections of these windings. There are two types, one is lap winding and another one is wave winding. Here to this poles we are going to connect the field windings like this. So the positive terminal, if you are going to take, this will be the negative terminal. So you are going to connect So this is how the connections will be there. So by giving DC source, you are going to create the magnetic field. Here that rotating part will be there. So what will happen when the conductor is kept in the magnetic field, the force will be experienced. That force will cause the rotation of this armature. So that is how the motor will work. So you see here in the construction feature, so here there is a stator. So this we will consider it is a frame. Okay. So here pole shoe is there. So pole core, and then here field winding we are going to connect. So are wound. We can say it is wound on the field windings are wound on the poles, and then this is the armature core. I already told you this, like this the armature is laminated. Okay. So you can use many number of such parts to create this armature core. So armature windings are, you are going to put the armature conductors in this slot, and then you are going to connect depending on lap winding and wave winding. In small machines, this ball bearings are used on both the sides. In large machines, rolling bearings are used. This bearings are mounted on the shaft, and also commutator is mounted on the shaft. This brush I already told you, this will collect the current. So these are fitted on the split rings. Okay, commutator will convert the AC current into DC. That's why this is called it as DC machine. See some of the figures, how exactly it looks like, that is commutator bars. So here this, see the commutator windings, how exactly you are going to consider this. Here commutator bars, and then armature windings, how exactly you have put it in these slots and then connected. So this represents the armature, that is rotor, and then you see how exactly it looks like. At the end, at both the ends, so you are going to use end rings to fit this. Okay, and this is the shaft. See here, this is the stator frame. For supporting, you are using this end plates. Okay, so this is the mechanical support to the field system here. Okay, this is the armature, this is the, and this armature is mounted on the shaft along with commutator and brushes. Okay, this is how the DC machines looks like. See the sectional view of DC machine. I already told you this is the pole fitted to this frame. Okay. So here you are going to supply the DC source, that is called excitation. Okay. When you are giving this excitation supply to this field winding, then the field will be produced. There are 4 poles in this, north, south, north, south. Okay. This is the armature armature is slotted on the outer periphery. Here the conductors are placed. I already told you that the conductor under the influence of north pole, you are going to connect to the conductor under the influence of south pole, and then similarly under the influence of south pole you are going to connect under the influence of north pole, like that you are going to connect. So, you are going to make the turns and then armature windings, okay. And then here the yoke will give you the magnetic path, that is for the magnetic field. Then when the conductor cuts the magnetic field, then the EMF will be induced, okay. This is a commutator part. This is how the commutator looks like. These are the brushes. See, this is how that when you are wounding this magnetic, that field windings, okay, and also when you are supplying by the external source. So, this is how the motor looks like. The constructional feature of both motor and generator is same. Interpoles, here one extra part is there, that is in interpole. So, you are going to use this interpole to reduce the armature reaction effect. So, the main parts in the construction of DC generator are, I already told you, this field system is required, armature core, this is the rotating part, this field system is the stationary part, then the armature winding, then commutator, brushes. So, this is how, see, this is the commutator part, and then windings are connected. I already told you that the windings, how exactly you are going to connect. The conductor under the influence of north pole, you are going to connect to the conductor under the influence of south pole. This is how it is connected. There are two types of connections. One is lap winding connection and the one is wave winding connection. Lap winding connection you are using for high current applications, then wave winding connections you are using for high voltage applications. I will tell you that why you are going to use. The field system, it is for uniform magnetic field within which the armature rotates. So, when the armature rotates in the magnetic field, the EMF will be induced due to relative motion between the magnetic field and the armature. There is a change in flux linkages, the EMF will be induced. The EMF induced, E is directly proportional to rate of change of flux linkages, N d phi by dt. When we are expressing this, E is equal to minus N d phi by dt. This negative sign indicates, according to Lenz's law, the causes opposes the response, or response opposes the cause. This is indicated by the negative sign. The EMF opposes the relative motion of the conductor. Then electromagnets are preferred because it has high flux density. So, that is why you are using these electromagnets in comparison with the permanent magnets, and also they are cheap, smaller in size, produce greater magnetic effect, and field strength can be varied with electromagnets. Field system consists of yoke, pole cores, pole shoes and field coils. These all are stationary parts. So, this will come under stator. Then you have this armature core. As I already showed, the armature core is cylindrical. It is high permeability silicon steel stampings. So, that is what I showed here, and then it is impregnated. Lamination is to reduce, it is laminated to reduce eddy current loss. Then armature winding, I already told you there are two types. One is called lap winding, another one is called wave winding. I will explain to you how exactly you are considering that lap winding and wave winding. So, I already explained how exactly you have to connect the conductor under the influence of north pole into conductor under the influence of south pole. So, the conductor under the influence of north pole connecting to the conductor under the influence of south pole by using end connections. Here you are going to connect the south pole, that is the conductor under the south pole, you are going to connect it to conductor under the north pole like this. And these are connected to commutator segments. This is called lap connected. So, this type of connection, the lap winding connection, the number of parallel paths is equal to number of poles. Suppose if you are considering 4-poled machine, the number of parallel paths is equal to P, that is equal to 4. In case of wave winding, that is the conductor, here also you are going to connect the conductor under the north pole, you are going to connect it to conductor under the south pole. But you are connecting to the conductor which is under another north pole like this. So, the number of parallel paths in wave connected system so that is A is equal to 2 always. The number of parallel paths is equal to 2 under wave winding connection. So, why we are using this lap winding? Here we have connected, that is A is equal to P. The number of parallel paths are increased. Okay, if you are considering P is equal to 4, it will be 4, and if you are using that P is equal to 8, the number of parallel paths will be 8. So, here, so since in series circuit the current will be same. Okay. So, you are going to use this for high current applications. In case of this wave connected, the number of parallel paths is 2. The voltage will be same. So, you are going to use this wave connected system for high voltage applications, lap connected system for high current applications, and also these are the wave connected system. So, now see this, in case of lap winding A is equal to P, the armature windings are divided into number of sections equal to number of poles. In case of wave winding, it is used in low current and high voltage applications, the brushes used are 2. Next we will come to this commutator. I already told you this commutator converts that AC into DC. This connect with external circuit, converts AC into unidirectional current. It is in cylindrical in shape, made up of wedge shaped copper segments. Segments are insulated from each other. Usually we are going to use that mica insulation. Each commutator segment is connected to armature conductors by means of copper strip is called razor. So, the number of segments is equal to the number of coils. Carbon brush, I already told you, it is used to collect the current. Carbon brushes are used in DC machines because they are soft materials. It does not generate spikes when they contact commutator. To deliver the current into current through armature, you are using this. Carbon is used for brushes because it has negative temperature coefficient of resistance. It is self lubricating, takes its shape and improving area of contact. Next we will come to this EMF generation. So, I already told you that the required parameters for EMF generation is the magnetic field. So, and the total flux per pole in Weber, the total number of flux lines, then the total number of conductors placed in the slot, then P is the number of poles, A is the number of parallel paths, N is the this armature speed in terms of revolutions per minute. So, Eg is the EMF generated in any of the parallel path. So, when you are considering these symbols, then the EMF equation, see that flux cut by one conductor in one revolution means that 0 to 360 degree, it is total number of poles multiplied by flux lines. So, in one full revolution, the flux cut by one conductor is P into Q, and then flux cut by one conductor in 60 second is, that is P phi n divided by 60. How exactly is this? So, to complete one full revolution from 0 degree to 360 degree, so it is, since we are considering that is number of revolutions per minute. So, it is, when we are converting into seconds, it is RPS, number of revolutions per second. Then the total time you are going to take for one particular revolution will be, that is 60 divided by T, 60 divided by N, sorry. So, now we already know that the EMF induced is directly proportional to rate of change of flux linkages. So, here the total flux what you are considering, that is cut by one conductor in one revolution is P into phi. So, and then the time taken is 60 divided by N. So, d phi by dt, now it is P phi divided by 60 divided by N. What will be this now? P phi N divided by 60. So, this is how you are going to get that P phi N divided by 60. The average EMF induced in one conductor is now P phi N divided by 60. Now, there are so many conductors in each slot, and also, so number of parallel paths will be there. It is depending on the lap connected generator or wave wound generator. In case of lap connected generator, I already told you that the number of parallel paths is equal to number of poles. In case of wave wound generator, the number of parallel paths is equal to 2. So, when you are considering that full, the number of conductors in each parallel path, so you are going to consider the total number of conductors divided by the number of parallel paths. Now, EMF generated between the terminals Eg is equal to, that is average EMF generated in one conductor multiplied by number of conductors in each parallel path. So, you will get this Eg is equal to P phi Nz divided by 60A. This is the equation of EMF induced in the conductor. Now, we will solve some problems on this EMF equation. In the next class, I am going to teach you that how exactly the DC machines, that is a field winding and armature winding, is connected depending on the classification of DC generator. Before going to that, we will solve some problems on the EMF equation. Okay. In this particular problem, you see this, the problem is defined like this: in a DC machine, if P is equal to 8, means the number of poles is equal to 8, the total number of conductors is 400, then the speed of revolution, that is 300 revolutions per minute, and the phi, the flux lines, that is equal to 100 milliweber. Then calculate Eg with, first with lap connected and then with wave connected. Whenever you are considering the problems, first you read the problem thoroughly, then you collect the data given, you see that what you have to calculate properly. Okay. So, now we will collect the data given in the problem. P given is how much? 8. Total number of Z is equal to 400. Then N is 300 RPM. Then the phi is equal to 100 milliweber. Since it is given in terms of milliweber, you multiply this by 10 to the power minus 3, then you express this in Weber. Okay. For lap connected, I already told you that the number of parallel paths is equal to P, that is equal to 8. We know that the EMF induced Eg is equal to Zn phi P divided by 60A. When you are substituting these values, that is 400 into 300 to 100 into 10 to the power minus 3 into 8 divided by 60 into number of parallel paths is equal to 8, you are going to get the answer, that is 200 volts. Similarly, for wave connected, you are substituting A is equal to 2 for wave connected. You observe the values in wave connected, you are getting, see, for lap connected you are getting 200 volts, for wave connected you are getting 800 volts for the same values whatever it is specified here. In this itself you can observe that the wave connected machine is used for high voltage applications, lap connected machine is used for low voltage applications. So, this is what you can observe on this. Now, you see the problem number 2. In this, an 8-pole lap connected armature, it is mentioned in the problem itself, it is an 8-pole lap connected armature, has 960 conductors, a flux of 40 milliweber per pole, a speed of 400 rpm. Calculate EMF generated, that is Eg, and then if the armature wave were wave connected, at what speed must it driven to generate 400 volts. In the second case, they had given the generated voltage, you have to find out the speed. Okay. So, now the data given in this case, P is equal to 8, then the number of conductors is 960, then phi given is 40 milliweber. So, you have to convert this into Weber, multiply by 10 to the power minus 3, then the speed given in this case is 400 rpm, and it is given for the first case, it is A is equal to P is equal to 8 because it is lap connected, winding is lap connected. So, in this case you have to find out Eg, Eg is Zn phi P divided by 60A, substitute the values, that is Z is 960, N is 400, phi is 40 into 10 to the power minus 3, the number of poles 8, so 60 into 8. Here you can cancel this before itself you can cancel this to minimize the calculations, or otherwise you substitute. So, then the value will be, so you are going to get the value Eg is equal to 250 volts. So, this is for lap connected armature. In the second case, they have specified it is wave connected armature. Okay, in this Eg is specified, that is 400 volts. Okay, you have to find out the speed N. In this equation, to get this speed N, you have to multiply this Eg by 60A, that divided by set phi P. Then when you are substituting the values, that is given here, and also this Eg is 400, you are going to get, this is 156 rpm. The speed is now 156 revolutions per minute. So, now we will see the next problem. In this, a small variation is there. It is an 8-pole lap connected armature driven at 400 rpm. is required to generate 250 volt. Here this generated voltage is specified. The useful flux per pole is given as 0.05 Weber. If the armature has 150 slots, calculate a suitable number of conductors per slot. I already told you that here the armature is slotted. Within this slot the conductors are going to placed. Okay. So now it is given that there are 150 slots like this. Now you have to calculate how many conductors you are going to get. Okay. So in this given, since lap wound armature, A is equal to P is equal to 8, N is equal to 400 rpm, okay, phi is equal to 0.05 Weber, Eg is equal to 250 volt. Sorry, here I use the symbol N, it should be Z. So now by using this equation, Ec is equal to Zn phi p divided by 60A. Now you have to calculate this Z. Z is equal to Eg into 60A divided by N phi p. So Eg given is 250 volt and then multiply with 60, and since it is lap connected, A is equal to P, it is 8 divided by, what is the speed? 400 rpm, pi given is 0.05 multiplied by 8. So you are going to get this Z is equal to 750. What you have to calculate according to problem? You have to calculate the suitable number of conductors per slot. How many number of conductors is placed within this slot? In that case, so it is number of conductors per slot is total number of conductors, Z is equal to 750 divided by the number of slots given as 150 in each slot. So you can place the 5 conductors in this. In each slot you can place 5 conductors. You see that here it is slotted in the outer periphery. Okay. So now in this problem you have to find out how many number of conductors is placed in this slot. The calculated total number of conductors is 750. So now the number of conductors divided by the number of slots given, that is 150. 750 divided by 150, in each slot you can place the number of conductors you can place is 5. Last problem. So here in the next problem we have 4-pole generator with wave wound armature. So it has 51 slots, each having 24 conductors. Now you can calculate the total number of conductors by multiplying the number of slots and the number of conductors in each slot. The flux per pole is 0.01 Weber. At what speed must be the armature rotate to give an induced EMF of 220 volt? You have to find out the speed of the armature. What will be the voltage developed if the winding is lap and the armature rotates at the same speed? You consider the first case, that is in the first case it is given it is wave wound. Okay. In case of wave wound, so A is equal to 2. Usually you will use this generated EMF equation. Okay. P given is 4, S is 51, Z is equal to 24 into 51, phi given, that is a flux given is 0.01 Weber and Eg is 220 volt. You have to find out the speed. So after substituting all the values with A is equal to 2, you will get that N is equal to 540 revolutions per minute. So and in the next part of the problem, you have to find out what will be the voltage developed if the winding is lap and the armature rotates at the same speed. Whatever you have calculated the speed, at the same speed it will be, the machine will be lap connected. Now you have to find out what is the generated EMF. Okay. In case of lap connected, the number of parallel paths is equal to number of poles, that is equal to 4. Okay. The speed calculated when the machine was wave winding is 540 rpm. You have to maintain the same speed and calculate Eg by substituting the values in this equation. Eg is equal to 110 volts. Okay. This is how you have to calculate the required value. So first you collect all the data given in the problem, understand the problem thoroughly, you collect the data, then substitute in the equations to get the required value. Thank you. So, in the next class I am going to teach you the types of DC machines and also how exactly the windings, the field windings and armature windings are connected to the terminals of the machine.